Okay, folks, let's get started already because we have a fairly packed agenda. Welcome to the Internet Congestion Control Research Group, and thank you everybody for joining us here on this Friday of IETF week. Hey, Simone, my co-chair Simone is joining us remotely. All right. So this is a hybrid meeting. As you can see, people are in person on site or online. And if you are in person, please remember to scan the QR code that is displayed at the back of the room or join from the agenda link from your browser. And if you're remote, well, you're already joined. Either way, if you want to speak, please enter the queue first by raising your hand and then speak into the microphone in the room or use the audio button to unmute your audio. And also, please remember to state your name before speaking. The session is being recorded. And here is a reminder of our note well. A number of you would already have seen that a couple of times this week, but it reviews our policies that we operate under in the IRTF, which follows the same rules as the IETF regarding intellectual property. If you haven't had a chance to look at these, please make sure you read up on them on these slides or by looking up IETF Note Well online. We do make audio and video recording of our sessions, and we make those recordings available publicly. For example, you can find recordings of previous sessions on YouTube by searching for IETF and the session name. So please be mindful that if you speak at this meeting, you're going to be recorded. We also do have rules regarding the handling of photographic material, audio, video, as well as other personal information. And also we have a code of conduct and anti-harassment policies from the IETF, which also apply to the IRTF, including this session. So please, let's make sure that we all treat each other with respect and care. If you have any questions or concerns, please talk to us chairs or please contact the Ombuds team. You can find their information linked out from this slide set, or you can find it online. The IRTF is the Internet Research Task Force, and we are not exactly the same. We are not the IETF because the IRTF focuses on research and it is not a standards development organization. So even though, especially in ICCRG, a lot of our work feeds into standardization or specification work going on in the IETF, still the primary goal of this session is to promote research collaboration, teamwork in exploring research issues. So we are not a standards development organization in the IRTF, but we're excited to talk about internet-related technologies. So here's our agenda for today. And first, I will need a scribe for today. Would any of you be willing to take some notes, for example, in the notepad that is linked out from the tool, just for any questions and answers and discussion coming up during our session? Thank you. Is anybody else willing to take notes and help?
Gary would love to eat his lunch and then we'll help. Is that a good deal? If I eat my lunch and then help, would that work? We have a deal.
Thank you so much, Gary. Thank you. All right. We are about to have a couple of presentations, but first I wanted to briefly talk about the hackathon because we had a congestion control testing table at the hackathon where we talked about evaluating and testing congestion control using simulation, emulation, as well as A/B testing. And two major themes were to work on our tooling. For example, NS3 is one of our options as a simulator, which we would like to enhance to make it easier for everybody to test congestion control proposals. And then there was a lot of testing around the care for resume draft, which is currently discussed in TSVWG. So just as a quick showcase of what was tested, care for resume is a method to use saved path RTT and capacity information to increase C-wind when starting up a connection. So we would go through a couple of phases to validate that this cached information is still applicable to our current path and potentially speed up our connection. And at the hackathon, we had this lovely network emulation box to emulate certain delay and bandwidth, and we used two different servers based on PicoQuick and Quiche, together with a couple of browser clients to load a web page. And now I don't have the great video that we saw in TSVWG, so you would have to look at the recording of the first, I think, TSVWG session. But just to give people an idea, care for resume results in loading this web page slightly faster than without care for resume, and it does make a difference. I really like a good side-by-side comparison to showcase that congestion control proposals can be very useful. So if you are attending any of the upcoming IETF meetings, we are planning to have the congestion control testing table again at upcoming hackathons. So please consider joining us and testing congestion control with us. And now we have our first presentation, which is Michael's draft on pacing and transport protocols.
Thank you.
Thank you. Take it away.
All right. This is just a short update on this draft. I guess the first big difference to the previous version is the authors that you see on the first slide. Vidi and Michael are new to this, so this is a version where they have now joined us. What is this about? The idea is to give implementers guidance regarding pacing in general. How could you do it? And if you want to know how to implement pacing, I suppose the best way to do it is to look at what others have implemented and how others are doing this. That's the point here. We give an overview of how others implement it. The 0.0 version, which I presented the last time, already described Linux TCP in some detail and quick BBR. Linux TCP based on a long document that I've written, and this quick BBR based on open source implementations that Wes has looked at, Google's Quiche and Meta's MBFST. The news is we have these two new authors. Each of them has contributed a bit of text, not so much yet, but they're both planning to extend it. So it's a relatively high-level description of what Apple is doing and what FreeBSD is doing, and both are going to be a bit more detailed. For Apple, Apple leaves the decision on how to pace up to either a protocol or an application. I see a critical look. Yes, I will be happy to stand corrected. This is me rephrasing what Vidi has seen these slides as well. So I'm doing my best here to, depending on the type of application it is. For instance, a video streaming application will have a different way of wanting to pace packets than, let's say, a stream-based protocol such as TCP would. It's a private API since iOS 17 and macOS 14. And the application and or the transport protocol would compute and set a timestamp per packet. So the application is really in control here. The active queue management part of the system would then delay packets accordingly with a 3-second upper limit. That's pretty much what is written there now. And I hope I was asking for some more details, and I think she will probably be able to supply them soon. For FreeBSD, we have a bit of text now from Michael. So FreeBSD has 3 separate TCP stacks. There's the REC stack, the BBR stack, and I think the classic stack or whatever it was called. The REC, so I wanted to have a bit more details about the REC one. Generally, there is a function called TCP output that is called when a TCP segment is received or the application provides new data to send or a timer fires. This is underlined here because this is what the next text is about. When pacing is used, TCP output can also be called by HTTPS, which is this high-speed timer, high-precision timer system. HPTS, sorry, it's a typo here. So it sends a microburst and reschedules itself for being called again after the interburst send time using this timing system here. In the X stack, the application can set the pacing rate and the max burst size with TCP socket options. So this is something that's a little bit similar to the, well, apparently it's different in the details, but similar to the Apple method in principle, in that you leave the control up to the application. The stack then uses these values to compute the actual microburst size and interburst burst time, and HTTPS can handle many connections and has a way to allow for TSO usage. So this is all really pretty much about the complexity in this, and then also in the way Linux is doing, is about being dynamic in how much you hand over to TSO. The slower you send, the more control you want to have over the gap of data, and the less important it becomes to hand over a bigger bulk of data. The faster you send, you want to hand over a bigger bulk of data and let TSO do what it's doing. Main next steps is to get more details on these two, as already said. We got input from Ingemar about discussing the initial RTT estimate in 5G. He sent us a bit of text that we're going to include. Some discussion of interactions between TCP and application pacing. There was a paper coming out of Netflix called SEMI, where they looked at application layer pacing and smoothing out the traffic over, well, to avoid the bursts that you would normally have in video streaming, so that it becomes an upper limit for the pacer that is in TCP. And we're going to have a bit of text on that. Yeah, there are some other small fixes that we have mentioned on GitHub. This is the GitHub page. Feedback would be very welcome. At some point further down the line, it would also be great if we could be adopted. And that's all I have to say.
Wonderful. Thank you for bringing this draft. And does anybody have any questions or thoughts about pacing or specifically Michael's draft?
Yeah, ask me anything about pacing. Bring him on.
Pacing is good. Yes. Gary.
It was good, Gori. Thanks, Michael, for doing this. This is really good. We were doing a lot of work with Cloudflare Quiche and doing this careful resume, as we heard, and the pacing stuff killed probably about 4 weeks of our effort in this. So just since it's a research group, let's say why. The first one is all these QVIS accounting stuff that we have on QLog occurs much higher up the stack. So when you want to look at pacing and know whether it's right, you have to somehow tie in the wire image with what's actually going on in the application. And that is quite hard when you've got a Q disk in the middle and perhaps an Ethernet card trying to do things to help you. So this is quite difficult to debug is what I'm saying. So that might be something that's interesting to talk about. And the biggest learning outcome is it's difficult to debug, but you have to turn the wrong things off. So if you're using UDP, we found out that GSO offload really messed this up occasionally, which was a little bit surprising. But if you didn't enable your card to do things, then it ignored the TX time information in the packets and it worked beautifully. So debugging pacing is something that's really important to do and turning the right switches on, and it's not always intuitive. So thank you for the document.
So the common answer I give to people that make suggestions, such like you now did, is that I say we will be very thankful for a paragraph. You know, if you send us a paragraph as a text donation, I'll be happily accepting that donation.
I was saying it was good work, but yeah, sure, no problem.
Yeah, just because you experienced it, so maybe you have some of the details that I'm lacking, right? So.
Stuart Cheshire from Apple, not a question, just want to thank you for doing this work. I think it's really good. Sorry if my expression earlier made me think I was disagreeing with you. I wasn't. I was interested to hear what your opinion was, and I'm glad that Vidya is helping you. You're in good hands there, and she'll be a good contributor.
Thanks.
I Lars Egger, not a question to you necessarily, but I remember a paper, this is a research group from a while ago, that basically said something like, or it showed that application level pacing, if you did it at the application level, was basically to some degree undone by the kernel and the NIC. And I can't find that paper anymore. So I'm wondering if I'm envisioning it, if somebody else remembers that paper, can we find that? Because I think it sort of is very applicable, and you would want to cite it if we if I haven't like made it up in my head.
I hear this sort of thing from Gori all the time, but I didn't know there's a paper that says it. So that would
So
be
I
a
thought there was a
great
paper,
to have.
But you know, old people's memories, like mine, like if not, maybe somebody wants to write that paper. That's also a possibility, right? Since no, it was about pacing offloading. Oh, no, it was about application level pacing and how it doesn't work as well as you might expect it to work. Maybe because of segment offloading, but that's more detail than I remember, but could be.
I'd love to see that paper. I mean, maybe send it to the ICCRG list, I guess. Yeah.
Yeah, if anybody remembers this paper or can find it, please drop it in the chat, send it to the email list, or open an issue on the GitHub, please. Sounds like a fascinating paper. All right, great topic. If nobody else has any thoughts for now, we can move on to our next talk. Hang on, just gonna cancel this timer and do another one. All right, take it away.
Okay. Hello, everyone. I'm Emilia, and I'm from the Max Planck Institute for Informatics in Saarbrücken, Germany. I'm here to talk about work that was presented earlier this year at PAM in collaboration with my colleagues listed here from MPI and VU Amsterdam. Okay, so we have spoken a lot about BBR, and it's granted because when it came out, it was kind of a shift from how we usually do congestion control, in that it tries to maximize or optimize up to Kleinok's optimal point using maximum bandwidth and minimum RTT. And if you're using any of these services, chances are that you're probably getting data transmitted using BBR. And of course, the community appreciated that. And this year's SICOM, there was a paper that said that most of the popular websites are now using BBR. And there was another paper at the same conference that also showed that a couple of CDNs are also using BBR to save their data. So in this presentation, I want to focus on the new version of BBR, which was introduced last year at the IETF 117. And it was described as a minor evolution of V2. As a recap, V2 was a bit of a shift from the first version in that it reacted to loss signals and also reacted to ECN marks. So BBR v3 promises to have better throughput convergence, as well as better coexistence with loss-based algorithms, which has been kind of talked about a lot in the community, and other benefits like lower retransmissions, as well as reduced latency. Now, when you have a CCA that comes out, you're usually concerned about how to verify its performance. So some people use simulation or emulation, as discussed at the hackathon as well. And if you have some infrastructure, of course, you can have a test bed or A/B tests with your network traffic. But even with all these options, it's very difficult to know which scenarios to run, as well as which parameters to use in those scenarios. And even if you figure out some portion of this that you want to use in your test case, it's kind of hard to reproduce earlier results, or the performance that you see might not quite compare to what was seen in a different network scenario. And I know that there's ongoing work in this group right now with regards to RFC 33 bis. And so, for example, in this paper from IMC 2019, in a toy network setup where you have one BBR flow competing with 16 cubic flows, people found out that it will take up half of the bandwidth. And but this issue of a CCA behaving differently when it's run in a different network is not limited to BBR. There was also a paper that spoke about copper, in that in a jittery network, copper has some underutilization issues. So taking all this into account, what we wanted to do with regards to BBR-V3, we wanted to have a systematic approach in evaluating its performance, taking into account the kind of scenarios it will encounter in the environment into which it will be deployed, such as the internet. So we thought about what would happen when you have CCAs using the same flows interact, about RTT fairness, coexistence with loss-based algorithms, which, as I said, has been kind of a major talking point. And we also emulated some kind of real-world network traffic where you have a bunch of short flows interacting with long-lived flows. Okay, so with the options I gave earlier, we went with the option of a testbed because we wanted something that we could control ourselves, and also using off-the-shelf tools to kind of have emulate different buffer sizes as well as delays, and also something that can be reproducible by someone with access to the same limited infrastructure. So if you want to reproduce our results, please visit this URL. It's not visible now, but it will be on the slides. Okay, so let's go to the results. We have a bunch of experiments to kind of look at the scenarios that we looked at, but here I'll just highlight the interesting ones that we saw. Here we first started with this scenario of two flows competing against each other. And when they both start at the same time, everything is nice and peachy. So they're sharing bandwidth quite fairly. But of course, flows don't always start at the same time. So we had another scenario where we stagger the start time of the second flow. And here we notice that BBR-V3 has quite a long convergence time. You can probably eyeball here from the plot that it takes about more than 3 minutes to get to some fair share of the bandwidth. So yeah, the convergence time is quite long, but when we looked at the V2 and V1 results, this was not the case. With flows with different RTTs, here we did an experiment where we have one flow with a very long RTT versus one with a short RTT. And ideally, the throughput difference between these two flows should be zero or close to zero. So here I'm showing throughput difference on the y-axis versus an increasing buffer size configuration on the x-axis. And intuitively, and also what we know from the existing CCAs such as Cubic, the short RTT flow gets most of the bandwidth. But with the earlier BBR versions, it's the other way around. And we see the same behavior with BBR-V3. If we flip this to look at the fairness between these two flows, here on the y-axis, note that I'm showing the BDP configurations versus the different CCAs on the x-axis. We're showing Jane's fairness. Of course, closer to 1 is better. So for Cubic, we see that even though the difference between the two RTTs is quite significant, the fairness is not so bad compared to V3, for example, where the fairness is very much close to the minimum fairness that's expected. Or not expected, but yeah. If you decrease the gap between the two flows RTTs, you see that fairness is improved, especially at shallow buffer configurations. But as you increase the buffer size, then the fairness again drops. So the larger buffer sizes are not so uncommon in the internet based on what we saw. Okay, now we go to the coexistence with Cubic. I know this has been talked about a lot in this working group as well as the CCWG. So as a recap, this is how BBR V1 looked when competing with cubic. As a side note, the bottleneck bandwidth is 100 and the RTT for these flows are 100 milliseconds. And when we look at BBR V3, we see kind of a similar behavior. And so this is at 1 BDP, but if we look at the results over different configurations of buffer size, we see that at shallow buffers, of course, BBR is unfair. If you look at the throughput share, this is average throughput share at each buffer size configuration. With BBR V2, I think it was a bit more fair when competing with cubic, but with BBR V3, we see that the situation looks very similar to what we saw in V1. Right, so yeah. So the earlier toy example that I spoke about, where you have one BBR competing with multiple cubic flows, we also wanted to take a look at the similar setup in our testbed. So I will show a matrix of cubic flows on the y-axis, increasing cubic flows on the, on the x-axis, and increasing BBR flows on the y-axis. And we are looking at Jane's fairness here. So if you look at the first column here, the number, the bigger number, which also corresponds to the color, represents overall fairness of all the flows. But if you look at cubic's flow on the right side, it's very little. So in correspondence with what I showed earlier, compared to BBR's share. And if you look at when one BBR flow is competing with 5, you see that it gets about 80% of the link bandwidth compared to just 20% for the 5 cubic flows. So like I said before, with BBR V2, the situation was a bit more fair towards cubic. So you can see here the 5 aggregate cubic flows get a bit more of the share. And with V3, I mean, there's a bit of an improvement from V1, but still, I think it's not ideal for the cubic flows. If we look at the other side of the plot, where you have 5 BBR flows competing with 1 cubic flow, you might say, okay, the fairness looks a bit better here, but if you look at the share of the cubic flow, you will notice that it's very little. With regards to V2, I guess it makes sense that they kind of moved away from V2 because you can see it was getting killed by cubic. Yeah. So take here we also tried to enable ECN because we read that you could use it with TCP style ECN. So we tried that in our testbed setup, but taking into account what Neil said on Tuesday, that it probably doesn't work well with longer RTTs. So maybe this could explain the results here on the right, where, as you can see, the fairness when ECN is enabled seems to be worse. Okay, so now with the emulated real-world network traffic, here we used a Maui trace that we downloaded beginning of last year, I believe. And and then we used the traffic generator to run those flow sizes. Here I'm showing flow completion times on the y-axis. Please note the log scale. And we put the flow sizes in bins, which are on the x-axis. For FCTs, the lower the better. So here also in line with what I presented earlier, we can see that the FCTs for the BBR flows are much lower than those of cubic. With V2, I think the fairness was much better, especially at the at the shorter flow sizes. However, at the higher flow sizes, you still have a bit of unfairness. And with V3, it's nice to see that at the shorter flow sizes, there's fairness that's comparable to what we saw in V2. But with larger flow sizes, you still see a higher flow completion times for cubic. So this is like flows running, half of them are running with cubic and half of them are running with BBR. So in conclusion, sorry if I went a bit fast. In conclusion, we looked at several scenarios to kind of represent what we think is a systematic approach to doing this kind of experiments or tests to verify CCA's performance. And we saw long convergence time for BBRv3 when you have deep buffers. We also saw that this bias towards long RTT flows that we have seen with BBR CCAs kind of continues in V3 as well. And with regards to coexistence, we see that they still struggle to coexist with loss-based CCAs. And the tables that I showed earlier still indicate that there are people using loss-based CCAs in the internet, so we cannot completely ignore them. So yeah, we are very much still doing ongoing work in this area. And if you are interested, please get in touch or visit our website. Thank you.
Great. Thank you so much for this excellent talk. And we have a couple of people in the queue. Roland is first.
Oh, I'm first. Yeah, thanks for the great talk. Just one observation. So you also considered staggered flows.
Yes.
And I guess you started them, what is 15 seconds after?
15 seconds after the first one.
Yeah, so just one observation from our experience that we did also with BBR version 1, it's good to choose a time that is not a multiple of BBR probe RTT phases, which are 5 seconds. So this might come to different results. And we had a look into the queuing delay behavior of BBR. So you looked at the fairness, we looked at queuing delay. So we just submitted a paper, so that's not public yet, but it consistently creates queuing delay in the order of 1 RTT actually. So I don't know, I even for a single flow, so I didn't see that behavior for BBR version 1. Did you look at queuing delay also?
Not specifically, no. No, we didn't look at this, but I will take your comment about the staggering into account and double check.
So using 7 seconds or so would be, and see whether it makes a difference.
Yep.
So sometimes we saw it makes a difference also for fairness. Second thing, do you know how I didn't get any details about the replay of the Mavi trace.
Yeah.
So we found out that it makes a difference if you, let's say, make the flow sizes and the interarrival times independent of each other, then you reduce the burstiness of what you're replaying. So it's good to keep them together. But what I read from your paper is that you're using some kind of tool that probably keeps them together, right? So
no, the flow sizes are the same, but the interarrival times we scaled them up a bit because this was in the order of like nanoseconds, I think. But we have a test bed with 100 milliseconds, so we kind of scaled up the interarrival times to match that. Yeah.
Yeah, just suggestion to try to keep the distribution together as far as possible.
And with regards to the comment about the starting time, I will check, but it's kind of strange that it only behaves this way in V3, but V2 also has 5 seconds probing time, if I'm not mistaken. So, but I will check. Yeah, thanks.
I'm Stuart Cheshire from Apple. Great work. Thank you for presenting this. One small request, as this work continues, it would be great to see Prague included.
Okay.
I mean, this is really important because congestion control determines how well the entire internet works. So if we get things wrong, we can break things quite badly. I'm sure you know about Comcast rolling out L4S, and Apple has been working on L4S on the client side for some time. So this is not widespread in the internet yet, but we would like Prague to become widespread. So knowing now if it has any problems would be really important.
Okay, thank you. I'll take that into account. We do have ongoing work in this area, testing other algorithms. I can't really talk about it now because it's under submission. So yeah.
Lovely, thanks. Next is Ingemar.
Yeah, I believe I've done really interesting work, and I agree with the comment using including Prague also in. But another question is that seeing that you have 10 millisecond and 160 millisecond, I believe that is something that you picked, and I believe maybe I'm a bit spoiled. I live in the northern Europe. We have a very short. You really need to struggle to go beyond 20 millisecond RTT within Sweden. So. And I believe, was it rational having a 10 millisecond and 160 millisecond in this case? Is it due to that in some geographical places in the world that you have 160 millisecond RTT to, for instance, content delivery networks and that stuff?
Mm-hmm. So we based these values on kind of what you get from end user RTT measurements. For example, if you check on the RIPE RTT website, you can still get even up to 400 or 300 milliseconds delays. I mean, it's probably at the end of the tail, but you still get these amounts. The 160 milliseconds we used here, we based it on the common TCP evaluation suite. So we kind of went with the suggested parameter in there. But you still get high RTTs in the internet. Yeah.
Okay. And then there's a lot of discussion around which version of VCN is BBR version 3 using, and I leave it at that, and that's something I probably need to have it discussed offline.
Okay.
So if you look at the comments and later of the presentation, we'll get more information.
I'll take a look. Yes, it's V3, if I understood the question correctly. Yeah.
Right, there is an ongoing GitHub issue on the BBR draft, which was linked out in the chat, and I think that'll be a great venue to continue that discussion as well. Dig into the details. Okay, Alexander, is that you?
Hello, my name is Alexander Azimov, Yango. So I wonder, have you evaluated the use of BBR3 in low latency environment, especially data center environment with ECN?
No, we haven't, because we wanted to emulate internet type of scenarios. So we didn't test it yet in data center scenarios. No.
I would be very glad to see these results too. Thank you.
Okay, thanks. I'll keep that in mind.
Okay, next we have Lars.
Lars, it's slow to go to the mic. Hi. Yeah, great talk. Thanks for bringing it. As somebody who might implement BBR on the client side in a browser at some point, so what in your sort of zooming out, right? Is BBR ready? V3? Should we consider it for widespread deployment? Do we still so I know it's a hard question, and then maybe, but I was sort of interested in you had a succinct answer. Should we what should we do?
I mean, if we care about fairness to loss-based congestion control algorithms, then maybe not. I don't know, but I mean, it's not for me to say, right?
No, but it is for you to say, because you did a lot of work on this, and you certainly have a deeper understanding than I have. And so I want to hear from an expert what if I should still wait a little bit before committing engineering resources, which I think is what I'm hearing.
That's a mean question, but you're putting me on the spot. But
okay, it's fine to say you don't want to answer me. That's completely okay. I just figured I'll throw the question at you.
Yeah. I think in terms of fairness, I don't know if it's quite ready yet, because even if you're not comparing to cubic, but to, for example, BBR v1, I have it on my backup slides. We see that the fairness is not quite there. So V3 very much takes over, gets most of the bandwidth when competing with V1. So I would think there's still some work that needs to be done in terms of ensuring fairness between the different algorithms.
Okay.
So you see on the right, top right here, it's competing with V1, but yeah.
Okay, thank you very much.
Yeah.
And sorry for making you uncomfortable.
No worries.
Can I jump in
we
briefly?
have Matt next.
Is it possible to jump in briefly with a CCWG related
Okay, sure.
comment here.
Okay.
As a pair of chairs of CCWG, to Lars's point, this is absolutely something that you have a hand in deciding for people. So a great presentation. But I think one of the things here when we talk about should we wait to implement is no, but please also, help bring solutions and ways to improve this, because I think part of what we're trying to do is get this ready for large scale deployment. And so the first step to that is figuring out where we need to focus. And I think the next step to that is, come bring these things and help us make it better.
Okay.
All right, let's hear from Matt.
Okay, I would second that actually in a different way. The hard to implement part of BBR is all the framework and the plumbing and the measurement infrastructure, the pacing, and getting all that connected together correctly. The details of the measurement algorithms, which determine the personality of the protocol, are actually relatively lightweight. And so as BBR v3 evolves, if it evolves, porting any changes to BBR v3 into a BBR implementation is likely to be relatively cheap engineering. Excuse me. I'm on the tail end of a cold. What I really wanted to ask, the reason I raised my hand is, did you confirm that Cubic was not in Reno emulation mode? And did you run your suite, say Cubic between Cubic and Reno? Because, go ahead.
Yeah, we confirmed that it was not Reno emulation. We also have not in this presentation, not in this paper, but we have results where we compared Cubic with Reno. So
I'm curious how well Cubic and Reno compared, because we have field experience of rolling the entire internet from Reno to Cubic,
yeah,
or most of the internet from Reno to Cubic, and how badly did it hurt? Because I believe the fairness index for Reno versus Cubic is actually much worse.
yes, I guess that's why most people switched over to Cubic. Yeah, we saw that Reno was basically getting kicked out by Cubic, but I don't have the exact numbers or results right now.
In all fairness, Reno was incapable of actually filling many of the large pipes. And so in many cases, Cubic filled pipes that Reno couldn't fill. And so, BBR is not in that situation. BBR comes very close to being zero-sum game, in the sense that if I increase one flow, I decrease somebody else. The link is likely to be full at scale, and so the problem is harder. I will argue further down the line, if necessary, that a fairness index of 0.5 is actually good enough for the internet, because in fact, for most paths, the bottlenecks are at the edges, and it depends on the level of aggregation, but performance is quite variable, and we can't fix that. And with transactional data, the users can't see it. The users don't have an expectation for what the performance is. And sometimes it's slower than other times, and we experience traffic on the highway, and we know that commute times vary and load times vary. And anyhow, that's a different level, and it has to do with the fact that the bandwidth scales across 6 orders of magnitude. A factor 2 difference in performance is actually not that much out of 6 orders of magnitude.
Okay, thank you, Matt. And thank you so much, Emilia, for bringing this work. I would love to see us converge to a common understanding of, I guess, fairness, and how much fairness do we expect for BBR at some point. So discussion to be continued. Next, we are about to have a presentation on speeding up slow start. Madi, are you ready? I will pass slides control to you. So you should be able to compare your slides. All right.
Hello, can you hear me?
Hello, yes, we can hear you now.
Hello, everybody. I'm Mahdi, a recent PhD graduate from the University of Otago. Today, I'll be presenting our project SOS, which is a collaborative effort with Haibo Zhang, David Ayers, and Abbas Al-Ghaoni. Every TCP data transfer begins with this question: at what rate should data be sent? To estimate this rate, TCP employs a slow start algorithm. It initiates data transfer at a low rate and then doubles this rate exponentially until it achieves a reasonable estimate. Thereafter, it enters the steady state to fine-tune the rate and send the remaining data accordingly. In this talk, my focus is on a slow start. A slow start presents two issues that are notable in today's network with large bandwidth delay products. The first issue is its slow and sluggish start. This often results in bandwidth underutilization. Conversely, a slow start can rapidly expand congestion window beyond network capacity in a single round-trip time. This rapid increase in congestion window can result in a significant buffer overflow. Several solutions have been proposed to mitigate these two issues. For instance, high start, which is integrated into the cubic algorithm, tackles the second issue by terminating exponential growth before severe congestion occurs. However, proposed solution for the underutilization issue either only work in specific situation or require network assistance. This slide shows one of our real-world experiments where a PC in New Zealand downloads a file from a server in the United States. As you can see, the number of in-flight packets shown in blue increases exponentially, and in the steady state, it oscillates around congestion window star. In this presentation, CWD star is congestion window size when optimal rate is achieved. Please note that the amount of total delivered data shown in brown here linearly increase at the rate theta in the steady state. This is because the bottleneck link is saturated. We added this dashed green line to represent a hypothetical scenario where the delivery rate is theta right from the start. This green line highlights the capability for delivering a larger amount of data during the initial phase. For example, in this test, delivering 5 megabytes of data takes almost 3 times longer using a slow start compared to the hypothetical scenario. This is shown by the dashed black lines. So an improvement in early round-trip times can reduce flow completion time, which is notable in delivering small data objects such as web pages, photos, and videos. We switched the congestion control algorithm from cubic to BBR-V2 and repeated the test. As you can see, a notable gap still exists between the actual delivery and the optimal delivery. And this slide shows dynamics of congestion window for 5 separate flows sharing the same bottleneck link. The fifth data transfer initiates after the link has already been saturated by the other TCP flow. You know that the cubic is sensitive to packet loss. So cubic terminates the exponential growth upon detection of the first packet loss. Here it is shown by the red circle. The cubic's early exit from slow start delays achieving a fair share of the bottleneck bandwidth and optimal delivery rate. To enhance the delivery rate during the slow start, our proposal accelerates the growth of congestion window in early round trip times when it seems safe. In a slow start, the growth factor is always 2. This means that congestion window doubles each round trip time. Please see the gray curve. However, our solution SOS employs a growth factor of 4 when the exponential growth is expected to continue in the next round trip time. And we have proposed the general case when it uses a greater factor when the exponential growth is expected to continue in the next n round trip time. This allows SOS to quadruple congestion window when it is significantly below congestion window star. Otherwise, it follows the traditional slow start by using a growth factor of 2. Our first challenge here is designing a method by which SOS can predict the continuation of exponential growth in the next round trip time. To address this challenge, SOS relies on a refinement of high starts criteria. In essence, to accelerate the exponential growth, SOS employs a modified version of high starts criteria. This high starts criteria is originally used to terminate the growth, but we use it to speed up the exponential growth. It uses the length of act train and observed queuing delay for the prediction. Because of time limit, I didn't include the flow chart and equations on this slide. Please refer to the paper if you would like to know more about how SOS makes this prediction. In our experiments, we observed that an acceleration in congestion window growth can result in burst and packet loss. To prevent these issues, the second challenge involves controlling the transmission of additional data packets. To this end, SOS employed a combination of ACK clocking and packet pacing techniques. ACK clocking mimics a slow start and sends 2 packets upon receiving 1 acknowledgement. This helps maintaining high start functionality and the estimation of the growth factor in SOS. In the pacing period, additional data packets are spaced out to reduce the buffer pressure. Let's use the example and visualize packet transmission in SOS. In this figure, you can compare the growth in slow start and SOS. When SOS is in use, the growth factor is 4 in the second and third round trip times, and it is 2 when congestion window is getting closer to its optimal value, congestion window star. I mean, round 4. As shown by the yellow shaded area in the below figure, SOS also employs guard intervals. This helps to ensure that the pacing period shown by pink area doesn't affect the clocking period and high start functionality. We have implemented SOS in the Linux kernel, and it is available as an open source project on GitHub. Being a sender-side mechanism facilitates SOS feature-wide deployment. It extends the memory usage by only 40 bytes for each TCP connection, and SOS also has a low CPU usage. For testing SOS, we use a diverse set of cloud servers and off-the-shelf hardware. As shown in this figure, our internet-scale testbed consists of servers hosted in 7 different geographical locations, and their clients are in Sweden and New Zealand. Clients are connected to the internet via different link types: 4G, 5G, Wi-Fi, and Ethernet. This combination forms 28 testing scenarios with different round trip times, different bottleneck bandwidth and buffer sizes, and different cross-traffic patterns. We also use a local testbed for testing the algorithm under a specific situation and extreme conditions. Similar to the previous talk, our local testbed is a dumbbell topology consisted of 5 pairs of clients and server connected via 2 Linux routers. In one of our experiments, a 4G Android smartphone in New Zealand downloads a file from a Google Compute Engine in the United States. As shown by the red curve here, congestion window growth is faster when SOS is enabled. So optimal congestion window is achieved earlier when SOS is on. However, the accelerated growth doesn't result in extra packet delay. This is shown by the black and gray curves. Using data from the same experiment, we plotted this figure. As expected, total delivered data is higher when SOS is enabled. For example, as shown by dashed black lines, a 2 megabyte data transfer takes 2 seconds when SOS is off, while it takes almost 1.2 seconds when SOS is on. And please note that both curves grow at the same rate theta once the exponential growth has ended. And this slide presents 2 of the experiments we conducted to evaluate improvement in flow completion time. And here our server is hosted on a Google Compute Engine in Tokyo, and the clients are in Sweden. And please note that the curves represent average values across 50 iterations with a shaded area. This shaded area shows standard deviations. And after reviewing all the results, we observed that SOS consistently outperforms both BBR and cubic, although the performance advantage was not significant in a few cases. But we haven't seen any negative impact on the performance of TCP flows. We found that higher round trip times and bottleneck bandwidth results in greater flow completion time improvement. Throughput, performance evaluation, and packet loss. Throughout the experiments, we observed that packet pacing reduces burstiness and buffer pressure, which in turn leads to a reduction in packet loss rate. That's why BBR exhibited a lower packet loss rate compared to cubic, regardless of SOS is on or off. And we also observed that enabling SOS reduces cubic's packet loss rate on average. And this figure compares packet loss rate in one of our experiments, a lower loss rate for small size flows. And this slide presents one of the experiments we conducted to investigate the fairness the impact of SOS on fairness. In this particular test within our local testbed, a new TCP flow competes against 4 existing flows for the bandwidth. And we used a fairness index and observed that it is higher when SOS is enabled. We conducted this test across various buffer sizes and minimum round trip times and discovered that although SOS enhances flow completion time, it doesn't compromise fairness. And in another experiment, we assessed the stability of a large flow competing with a group of 12 smaller flows for bandwidth. We observed that enabling SOS for the small flow didn't affect the flow completion time of large flow. We repeated this test with BBR and varying minimum round trip time for the large flow. Additionally, we tested with different bottleneck buffer sizes. And after reviewing all the results, we found that enabling SOS doesn't adversely impact the stability of large flows. And because I'm running out of time, I'm stopping here and happy to hear your feedback and question.
Wonderful. Thank you, Madi. We have Jana in the queue.
Jana Iyengar, Fastly. Thanks for the presentation, Madi. I may have missed this, but how do you set C1 star?
We don't use exact value for CWD star. I used, for example, in the in this figure, congestion window star is calculated when the experiment has finished. So I just draw this dashed green line for the hypothetical scenario to show you that a big gap exists between the optimal delivery rate, if we can achieve the optimal delivery rate right from the start. You know, in the algorithm, we don't calculate congestion window star.
Okay, can you go to the next?
In this next one.
The one after this, the one where you talk about the key idea.
This one.
Right. How do you know whether to expect congestion window to grow in the next RTT?
Yeah, exactly. This is the key idea. So, you know, higher start uses two criteria to stop the congestion window growth. So based on that, we used to predict. I didn't include the math here, but the key idea is quadruple congestion window if the exponential growth is expected to continue in the next round trip time. How SAS predict this based on the criteria that HighStart uses to stop this? If I can share my.
And I don't want to take up a lot of time. What's missing for me in this is first that how do you compute when to quadruple and when to double? The second thing that's missing for me is why 4? If you know that your C1 growth is going to continue to the next RTT and you know how far you can go, you could just you could do 8, 16, 32, or even go straight up to the window that you believe you should get to because you're pacing anyway.
Mm-hmm. So first of all, the answer of both questions are described in detail in our paper. In the paper presented in SIGCOMM 2024, we included an algorithm for the general case when we can predict the next n round trip time, the growth in the n round trip time. But for this specific implementation, I used just next round, and because in my experiments, I found that a greater growth factor is not a general, it's a point solution. It works in some specific scenarios, but it doesn't work in others.
Okay, so what I'm hearing is the details of the algorithm are in the paper, and you're saying 4 is somehow a magic number.
No. You know, our experiment is based on 4, but the presented algorithm in the paper is for even greater than 4, like 8 or 16.
Okay. I understand.
Yes.
Thank you.
Okay, let's hear Roland, and then we will move on.
Yeah, Roland Bless, KIT. Thanks for the presentation. I was wondering in, I guess, slide 2 also, there's the RTT shown, and sometimes I always get a little bit nervous if this isn't to be considered as being variable over time. So is it the RTT min, or is it the effective RTT including the queuing delay? And I was wondering how this works in case the bottleneck's already saturated. So I hadn't time to read the paper, but that just one question that came to my mind.
Yeah, SAS uses the effective RTT because it doesn't have minimum round trip time when it starts. And if the buffer is saturated, so it needs to put more pressure to reach its own share of the bottleneck bandwidth.
Mm-hmm. Okay, thanks.
Okay, great. Thank you. Let's move on to our next presentation. And I will pass slides control to Akshay, you have slides control now, and let's see if we can hear you.
Can you hear me?
Yes.
Great.
We can hear
Okay.
you well. Right, take it away.
Fantastic. This is work that was presented also at SIGCOMM this year. It is, of course, joint work with all of the various people that you see on the slide across the number of institutions whose logos you can see. If you are curious to know what the logo is for a given institution, please look at the paper. Okay, so I have to click the arrow here. Yeah, let me start with the state of the world in congestion control today, right? So the norms and community enforcement that we very traditionally had in the past that govern how we adopt congestion control protocol have, if you ask at least some people, including me, given way to more of a wild west of congestion control algorithms. So as an example, let's consider a few recent congestion control mechanisms which originated in industry, right? So industry practitioners designed these algorithms to optimize the throughput and latency that their applications experienced. So of course, what came after this was the backlash from researchers, including us in this room, who have analyzed these new algorithms, and especially in the most well-known case of BBR, as we heard earlier today, found that the algorithms don't compete fairly for throughput with existing commonly deployed algorithms like Reno and Cubic and so on. And it's important to acknowledge in this case with BBR that the authors have responded to these concerns with changes to the algorithm, right? We're now on BBR v3, which has some different set of fairness properties than previous iterations of BBR. But the real point that I want to make here is that the internet is clearly no longer in some sort of regime where concerns with TCP fairness are able to prevent CCA's deployment before it's actually deployed, right? We're now reacting to algorithms that we see deployed post hoc. So if TCP fairness is no longer effective, what mechanism should we be using instead? So the goal that we propose in this work is what we call CCAI, or Congestion Control Algorithm Independence. So what we mean by this is that the throughput a given internet flow can expect shouldn't depend on the interactions that that flow's CCA has with other flow's CCAs. Oops. So one thing to discuss is what impact providing CCAI will have on the design of these congestion control algorithms. So currently we can think of a CCA's job as comprising three things, basically. So first is discovering the available bandwidth and using as much of it as possible. Second is minimizing the queuing delay that the traffic experiences. And then third is doing exactly this relative bandwidth allocation task of sharing the bandwidth fairly with other flows. And of course, as we've seen in recent work, achieving this fairness property can be quite hard. So with CCAI, algorithms wouldn't have to worry about this fairness property anymore, since bandwidth allocation is now going to be handled by an external mechanism. And as a result, embracing CCAI in the internet would recognize this explosion of interest in new CCA designs that we've seen in recent years and allow users to design CCAs that focus on the core trade-offs in CCA design that we've seen people optimizing for rather than fairness, right? So trading off throughput, latency, and sensitivity to changes in available bandwidth. So probably the simplest path to CCAI would be to use a very traditional idea, which is isolation between flows, which is implemented with a mechanism such as fair queuing. Instead of treating our queue as a single queue, we can treat it as multiple virtual queues with a virtual queue per flow. And if we divide the link's bandwidth between these virtual queues, then the CCA the flows use is no longer going to affect their bandwidth allocation as long as they have a packet in the queue, right? So are we done now? If we want the internet to provide CCAI, should we just advocate for the universal deployment of fair queuing? And unfortunately, while this solution works technically, it doesn't work economically. And we've known this for a really long time, in fact. This is because the internet is an economic system as well as a technical one. And Bob Briscoe famously observed this in his 2007 IETF talk, as well as a CCR paper, in which he pointed out that flows actually have nothing to do with internet economics. And what we mean when we say this is that flows as a concept are unrelated to the economic arrangements that make the internet work. So if we want to advocate, or if we were to advocate for the universal deployment of fair queuing, that isn't something that we should expect to happen naturally, right? We should expect to encounter a lot of resistance to it, since there's no economic incentive for that to happen, right? So we need another solution instead. So to come up with a solution that does fit the internet's economics and is therefore something that we can reasonably advocate for deploying, we should understand exactly what these economic properties are. And there are two properties that are the most relevant and that I want to talk about today. So the first is the pay for access model, in which we pay money to a provider in exchange for access to that provider's negotiated internet routes. The second property is the recursive structure of these access agreements, so that your provider will in turn have an economic agreement with another provider, and that eventually gets you the access that you actually want. So the key idea in this paper is to take the economic properties that we just discussed and use those economic properties as the principles for internet bandwidth allocation. So if we allocate bandwidth to traffic according to these principles, rather than the existing framework of TCP fairness, then we'll have achieved our goal of congestion control algorithm independence, because that's the mechanism that we use to allocate bandwidth. So the first principle that we developed is called relative rights. So if two customers of the same provider have different economic agreements with that provider, in cases of congestion, the provider should allocate more bandwidth to the customer that pays them more. So we can consider this principle in terms of when there is a congestion event and we have to drop packets, we should drop packets corresponding to the economic agreements that we have. So this principle draws from the differential access that we can already achieve today, where if all senders were to blast traffic, they would achieve different throughputs due to the access limitations that they already have today that govern how much traffic they're allowed to send. And the main difference that we propose here is that this differential access be not only at the edge, but enforced by access speed restrictions, but also throughout the internet. Your rights should sort of follow you throughout the internet. So this the rights following you throughout the internet is exactly the second principle that I want to talk about. So remember that under principle 1, provider A here only enforces relative rights if there's congestion in provider A's network. If the congestion is elsewhere, principle 2 says that we should enforce these rights should follow you. So to see what I mean, let's consider this case where provider A isn't experiencing congestion, but provider B is. So when provider B drops packets, it has to choose between provider A's traffic in the aggregate and then customer 3's traffic. So under principle 2, it should additionally consider which part of provider A's traffic to drop, right? Customer 1 or customer 2's traffic, depending on that recursive relationship with provider A. So finally, we need to also handle cases where there are no relevant economic agreements for us to lean on. So how should we allocate bandwidth in these cases? So for example, in this slide, customer 1 is running both application 1 and application 2, and we need a way of deciding which application's traffic is going to get dropped when there's congestion. So our answer is principle 3, which is that there is no internet-wide answer to this question, and thus we should leave the answer to independent point domains, which can decide the relative value that they derive from the traffic of various applications that they want to run. And I don't have time in this talk to discuss how the customer might go about answering this question, and I'll refer you to the paper instead for a discussion of the possibilities here. So if we put these principles together, we can derive a bandwidth allocation framework that we call RCS, or recursive congestion shares. And these three principles combine into a mechanism that actually looks a lot like hierarchical weighted fair queuing, which is a very popular idea in the literature, except what we're doing that is different is that we have very specific guidelines on how to set these weights in the weight tree for hierarchical weighted fair queuing. And I'm not going to discuss how we implement hierarchical HWFQ in this talk. There's a lot of work that's been done on this in the past. And instead, I'm going to focus on how well RCS does as a bandwidth allocation mechanism. So since we base it on economically derived principles, RCS as a framework is what we're going to say is definitely economically consistent with the internet. So now we can ask the question, does the bandwidth allocation framework that we've just implemented achieve the CCAI goal that we set out to achieve? And interestingly, in the answer to this question in the general case is actually no, it doesn't. So we've generated counterexample topologies with, for example, cyclical interactions between traffic as they traverse the network, in which following RCS actually doesn't provide CCAI. So there's more details about these counterexamples in the paper. But instead of asking about all possible topologies, we can determine whether the CCAI property holds for many topologies, including those structured similarly to the internet topology that we can observe today, as well as random graphs. So the way that we're going to determine this is using game theoretic analysis, where the topology and the weights are the game and individual traffic sources are the players. So the high level question that we're asking is whether there exist player strategies, which are kind of analogous to really aggressive CCAs, that enable the player to manipulate the outcome of this game and get more bandwidth allocation for themselves. Okay, so this table shows one aspect of that analysis. So without getting too deep into the game theory analysis, and I'll refer you for details to the paper, we can classify topologies as providing CCAI or not providing CCAI, right? So in the overwhelming majority of cases that we evaluated, including both random topologies as well as those that we constrain to have a structure that's similar to the graph structure that we can measure from CAIDA's AS relationships dataset, RCS does provide CCAI in these cases. So for the CAIDA sampled topologies, in fact, we couldn't find a single CAIDA sampled topology that didn't provide CCAI under RCS. For random topologies, we did find some cases, about 5% of the ones that we tested, in which there was a theoretical lack of CCAI. So when we investigated these cases a little bit more closely, we found that the average gain that an aggressive CCA would be able to achieve on these topologies was about 0.01% additional bandwidth. So in other words, in almost all cases, and in every case of the ones that are representative of the internet that we actually have, RCS does provide CCAI. And even when you relax this assumption of realistic topologies and go to random topologies, when CCAI is violated, the gain that an aggressive CCA can expect is extremely small. So we've shown that for most topologies, the expected gain from using an aggressive CCA in RCS probably wouldn't merit the effort of developing such an aggressive CCA. So next, I want to move from theoretical results to practical ones, right? How will real CCAs that we actually have today behave if we were to use RCS, and do the same findings apply? So we find using emulation-based experiments that actually, yes, the same finding is going to apply. So first, when we implement each of these mechanisms in our emulated topology, we're going to sample another 10 topologies from our CAIDA dataset for this experiment. And then for each of those topologies, we're going to run 10 experiments where each flow gets a random CCA assignment. And then we can ask whether the allocation that a flow gets within a topology, but across CCA assignments, remains stable across the topology, right? If the allocation isn't stable, then we know that there's no CCAI, since the random variation in CCA assignment, like whether it got Reno, cubic, BBR, or whatever, across those iterations caused a difference in the bandwidth allocation, right? By definition, that means it wasn't the bandwidth allocation dependent on the CCA. So we find in this graph that, as expected, using traditional FIFO scheduling doesn't provide CCAI. But using fair queuing, as well as RCS's HWFQ mechanism, do provide CCAI. And we can see this because the spread in bandwidth allocations across CCA assignments, the P95 minus P5 bandwidth that it got across these iterations, the spread was very low. So the next question that we can ask, given that we know the allocations were stable for two of these configurations, is whether the allocations match the ones that we predicted using our game theoretic analysis. So are the allocations consistent with RCS's model of the internet's economics? So here, for simplicity, I'm only going to show you results for fair queuing and RCS, since those were the only results that got us CCAI. So we're going to look at how far, in terms of squared error, the allocation distribution was from what our economic model predicted that it should be. Okay, so first look at fair queuing. We saw on the left side that fair queuing offered CCAI, like we talked about at the beginning of this talk. And just like, again, we talked about on the beginning of this talk, on the right side, we can see that the allocations that it achieves diverge from what our economic models predict that it should be. And this matches the same point that Briscoe made back in 2007, right? Flows aren't economic units, so we shouldn't expect flow rate fairness to give us allocations that are compatible with an economic model of internet dynamics. And we can see that our implementation of RCS does quite well on both of these graphs. It offers both CCAI as well as returning allocations that are consistent with this economic model. So There are a few issues with RCS that I haven't discussed in this talk. The first is practical concerns around implementing, deploying, and scaling RCS. I'm not going to talk about these in talk. We can maybe talk about them afterwards, but the paper does have a discussion. The high-level takeaway is that we believe there aren't major technical hurdles to deploying this from a technical standpoint. A second important aspect of RCS to consider is the fact that it establishes a relationship between bandwidth allocation and economic arrangements, right? This is not something that we've had traditionally. And it's reasonable to ask whether this bandwidth allocation mechanism is an equitable one and whether it conforms to our expectations of net neutrality in the internet. So we discussed this in the paper, but we believe that RCS is in fact compatible with generally accepted notions of net neutrality, especially considering the economic structure of the internet and tiered access plans for internet access today. And finally, I want to discuss RCS's deployment prospects. So we do acknowledge that we're proposing a rather big change in the internet architecture in terms of how we allocate bandwidth, and we're realistic that the chances for deployment are relatively low in the near term. But one of the benefits of RCS is that it offers a way for domains to sell a tangible product to their neighboring domains that they can't sell today, right? If you sell these relative rights, you're offering a specific service, and the domains that you sell that to can then resell that product to their neighbors. So as a result, and we show this with the experiments in the paper, even if only a few domains along a path deploy RCS, they can significantly increase the level of CCAI or isolation along the path. So given the ability to sell service, as well as the fact that we can provide an incremental benefit, we do think that RCS is a practical proposal that could feasibly be adopted. Thanks so much for listening to this talk. I'm happy to take questions either now or over email afterwards, and strongly encourage everyone to read the paper for more details.
Great, thank you. We already have a couple people in the queue. Jörg is first.
Hi, Jörg. Thanks so much. Very cool. I have a simple question, or maybe not so simple question. Let's see. You had a bunch of dollar signs, sometimes multiple, sometimes single ones in your overall exchanges or associated with traffic. Now, dollars may be worth different amounts relative to different economies. The internet is a global area. Do you have thoughts on how you could cope with these imbalances that you would find in gross domestic products and so forth?
Yeah, this is a good question. I don't think I want to be very clear that we're not proposing strict proportionality in terms of dollar amounts for bandwidth allocation. There is definitely some kind of non-linearity that is required to make this fair, and that's not something that we've thought super hard about, but is something that we need to consider moving forward. I do want to point out that most of the time, when you're considering whether to drop packets from a flow or between two flows, that decision is happening at the same level of hierarchy in your bandwidth tree. So those dollar amounts are comparable to each other. It's just between the levels of hierarchy in different parts of the internet. That's maybe a relatively more rare case that you need to consider. Does that make sense?
Cool. That makes sense. Cool. Thanks.
Hi, Lars. That was a nice talk. Thank you very much for coming and giving it. So as we mentioned Bob Briscoe a number of times, and Bob talked about this problem a lot, right? That's those of us in the IETF remember. But he also had a bunch of proposals for solutions, namely re-ECN and the work that we then did in Connex. And I wonder, since I didn't read the paper, but I looked at it and I grabbed for re-ECN or ECN, and I don't see that mentioned very much. I wonder if you had sort of feeling how that work that Bob did applies to the problem space. Is that a contender for a solution here, or would it not be suitable for reasons that I don't understand?
Yeah.
Thank you.
So the re-ECN work is, at least in my thinking, more under the sort of umbrella of network utility maximization. And network utility maximization, we do discuss in the paper, and our sort of argument against it is that it's like a very drastic change in bandwidth allocation. And RCS is our way of proposing a way that is less of a drastic change. Like, you still can keep your congestion control. You don't have to have fine-grained coordination with routers in the middle of the network to negotiate link pricing and all of these things, but you still get the isolation and CCAA property that we set out to try to achieve.
Yeah, fascinating work. I completely agree with your assertion that economic fairness is a better, in some sense, a better motivator. And I had the same questions as Lars did about re-ECN and Connex as possibly as a signaling mechanism. Am I mistaken? You didn't say anything about signaling.
Yeah. So the paper does have some discussion of what the signaling mechanism would be. It is sort of like, from the perspective of the paper, it's an implementation detail, and we were more concerned with evaluating whether this bandwidth allocation mechanism is a stable or a strategy-proof one. But that's totally reasonable as a direction for future work, is to figure out exactly how you would signal the weights.
The other deployment question is, what fraction of the internet runs in a mode where you need to worry about fairness? I mean, most in the Northern Hemisphere, most of the links are underloaded.
Yep. This is also a good question. I think what I would say is that even if you sort of don't need to care about fairness in terms of contention between control algorithms, I think rather than having an arbitrary mechanism for determining how much bandwidth you get, you would still want, it still provides value to you to have your bandwidth weights respected further on throughout the internet, right? Like currently, you can negotiate an access agreement with your provider, and anything outside that provider is just arbitrary in terms of what bandwidth allocation you're getting, even outside of fairness concerns. Whereas under this mechanism, your relative rights would be respected further on. The allocation would be less arbitrary.
Yeah, but in a lot of the Northern Hemisphere, particularly, the dominant congestion control is actually slow start. You never.
Yeah, I agree with you.
Okay, let's move to Jana and then wrap it up.
Hey, Jana.
Jana Iyengar, Fastly. Hi, Akshay. Thank you for the presentation. Just a few points, and I'll note them quickly. The first thing is Bob Briscoe has been invoked in the room, so I will say we miss you, Bob. I know you're sitting somewhere else and retired, but please, if you watch this video, we miss you. The thing I will note is that Lars mentioned re-ECN. I want to get to something here. It's fair to say that economic fairness, yes, we know this, that economic fairness is the fairness model that is in practice on the internet, but that tends to work in aggregates. Congestion control tends to, and I say tends to because re-ECN I think is an exception, that tends to work on the flow level. The problem here, one of the problems here is mapping from the aggregate to individual flows. Re-ECN actually gives you a tool that you can deploy in a decentralized way, where a network operator that operates their own switches can choose to do marking in the way that they want on various kinds of flow aggregates. It doesn't have to be a 4 tuple, it could be an aggregate that you decide based on your subscriber and so on. So I'll make that distinction that re-ECN is actually a mechanism. I think what you articulated here is an argument for why something like re-ECN should be deployed as against being an alternative mechanism, because I don't think you have a mechanism here.
Yeah, so I didn't talk about a mechanism in this talk. The paper does have a discussion of like the way I alluded to this in the talk is what I refer to as endpoint control, principle 3, and the paper does have a discussion of like my own past work on how to do this relative like flow-based mapping of flows to aggregates at the edge. That work is called Bundler. It was at Eurosys 2021. And the high-level idea is that at some point you have to decide what your edge is in RCS. And if you're at the edge, then you want to do endpoint control and use this edge-based traffic controller. If you're not at the edge, if you're in the core, then you want to use HWFQ. And we do support this like sort of dual mechanism way of mapping flows to aggregates and then taking the aggregates and doing this like hierarchical bandwidth allocation for them. Did that answer your question?
Partly, but I think the question stands of an analysis or comparison against re-ECN and why something would be fundamentally different. If it's only a mechanism difference, then the question becomes one of incentives and which mechanism is easier and better deployed. But I would encourage you to think about how the goals are different from that of re-ECN.
Yep, thanks.
All right, great. Thank you, everybody, for the discussion. And now we are about to have a panel discussion. I will pass it to Simone to introduce our panel. And then should I pull up the first slide set? Oh, cannot hear you yet, Simone.
You don't hear me.
Okay, I can hear Ingemar,
Oh, thanks.
but I cannot hear Simone. We'll pull up the first slide set already.
Who is first?
5G.
We had some
Okay,
preparatory
so
slides.
we are going to have two panelists, Ingemar and Robert, and both of them are going to give us a short presentation about some considerations regarding specific link types and congestion control, and then we're going to have a panel discussion. So Ingemar will go first and talk to us about 5G. And I'm not sure about the time limit, but let's do 5 minutes for each introductory talk.
Sure. I will try to not bore you to death with this. And because you're moving your changing the slides, or
Oh, I'm sorry. Yes, I passed slide control to you.
Yeah, you can go to the next slide here immediately. And
you can do it yourself now.
Okay. I believe this is about how 5G access and which is mainly the last mile access affect how you should look at congestion control, how you should what you should consider when you design your congestion control algorithms mainly. And it's a bit of a quirks and parts then that are associated to 5G and what you should do and what you should try to avoid to do mainly. And first, we have this matter of resource allocation, and what you typically have is that each user gets a share of resources. You can have divide it in time frequency blocks. Actually, you have for instance, for one 0.5 millisecond slot, you may have 100 resource blocks that are allocated to users, and that is shared equally, typically between users. And if you have two users in a cell, you get 50 resource block each. But that is not directly transmitted to bitrate, because what bitrate you get is depending on the channel quality that you have. So that's the number of resource blocks to scale with the channel quality, and that with a modulation and coding scheme that you currently can use without getting too much block errors on the radio interface. And that changes quite rapidly with the channel quality, and also if you have uplink transmission, it changes. You have power limitation. Typically, for normal telephones, you can have a 0.5 watts of power in an uplink to transmitter, and if you are far away from the base station, you end up in that limitation as well. So it's not only a rate limitation; it's a kind of a power limitation as well. So given this, that the resource allocation can change from in a couple of RTTs. For instance, if users add and leave the cell, and that you have varying channel conditions, you can see that the channel quality, the bit rate that you get through, that changes. And there is no way to try to push more, like if we have this TCP-friendly rate control that gives some slack. But when you're limiting the throughput, you need to abide to that. That is the general rule that you have. I can move to the next slide here. And then we have this discussion of throughput, and it changes on a short time scale. And you have fast changes in channel quality. It can drop quickly. And typically your congestion control, even if it's a L4S congestion control, it cannot track those fast changes. So you need to have some kind of a headroom. So you have a very simple trade-off generally. Either you keep large network buffers, perhaps 100 millisecond buffering, and you get a higher link utilization, or you allow small network buffers, but then you get reduced link utilization. You have to pick one. You can't get away from that because the laws of physics get in your way. And then also network buffering is not always bad, because in radio you have transport blocks. They are more easily filled, and you get reduced control channel overhead if you have data in the buffers. And also you have this issue that you have something that's called carrier aggregation, where you add carriers into to get a higher throughput. And in order to get those extra carriers, you need to have a certain degree of buffer occupancy in order to get that. If you try to stay at low bit rate, you don't get any additional carriers. And then there's something called multi-user MIMO that is more efficient if there is some slack to pick the right occasion to schedule a number of UEs. And delay properties, and that is something that can, if you're not careful about it, that can inflate the round trip time. And that is typically you have something that's called dynamic uplink scheduling. And also you can have something that you get the handover, retransmission, and measurement gaps when you have for interfrequency handover. And the outcome in 10 seconds of this is that delay is a problematic congestion indicator. So be careful when using delay in congestion control. And the good news is that you have L4S that is rolling out in for 5 years. So use that as much as possible. And so that's my time is out.
Do you want to take questions now, and then we have a broader discussion later? Maybe let's try
I have a
clarifications for the talk.
quick clarification question. Is this all 500 microsecond slot time that's sort of globally constant?
No, I believe it depends on. I mean, for typical, talk about mid-band transmission, that is 3 point something gigahertz transmission. Then you have 0.5 milliseconds time slots. But if you go into higher frequencies, then I believe it's 0.125 is the interval, the slot distance.
So it's a constant for a given version of the technology, but
You can say it like that, depending on frequency band. Then, so.
Great. Gori has a clarification as well.
It's a kind of clarification, kind of question, but it's just basically what happens when you have the more esoteric waveforms and we go for much higher frequencies, terahertz or whatever you want to call it, technologies where the propagation is different. How does that affect the things you've said?
I guess for higher frequency, you also you have larger issues with, like, for instance, foliage and things that get obstructed, and you can have a very quickly that the throughput drops. And another challenge with higher frequencies, you have a larger what's called attenuation with a distance, so we can have larger asymmetry between the downlink transmission and uplink transmission. And that can cause issues. For instance, the TCP-X in the uplink can have issues. So.
Okay, Michael, do you have a clarification?
Michael Welzel, I would like to, I agree that sometimes you need large buffers. I would like to say, or to add to this conversation, that I have long been annoyed with the fact that people conflate low latency with little buffering as a general thing, because there are things that require low latency, where low latency just translates into finishing the completion time of a flow very fast, as would be the case in, for instance, static web page download. These things are latency critical. They require low latency, but it's just about finishing the transfer fast, for which a large buffer may be quite okay, as long as you don't have bad interactions with other traffic. So I think it's important to keep that distinction in mind. Not all latency critical traffic necessarily needs a low buffer. It's just for interactive traffic that we really want this.
Yeah, agree fully.
Okay, and let's try to keep it to clarifications and questions. Stuart, did you have a question? Okay, let's move to the second kickoff presentation. And Simone, we can hear you now. That's great.
Yeah.
Did you want to add anything for right now?
No, I just want to thank Robert and Ingemar for accepting our dozens of emails and be here.
Yes, 100%. I think this is an excellent topic for ICCRG, and excited we're having a panel discussion. Now, Robert will tell us something about Wi-Fi.
Okay, hopefully everybody can hear me.
Yeah.
Yes.
Good. So I try to throw this together real quickly from a perspective of if you're doing congestion control, what are sort of unique characteristics of Wi-Fi you should consider or be aware of. Wi-Fi is listen before talk. So it has to do collision avoidance. There's no collision detection, so to speak. And that drives this EDCA, distributed access mechanism, which is a probabilistic mechanism. So just if you never transmit it, but just arbitrate it all the time on the best effort, it costs roughly 100 microseconds to access a medium. So that sort of limits your packets per second or your transmits per second to about 10,000, and that's with no payloads. So keep that in mind. And that's what also drives the next thing, which is aggregation. Since it's so costly to access a medium, you say, okay, when I do get access, I want to put 32 packets on the air or 64 packets. So you're trying to get as many on the air as possible. And something else to keep in mind, if you're doing packet pacing, you need to think about that these 3264As might actually be in your advantage because it's the TX opt that's you're trying to optimize at most times. Another thing to keep in mind is that at 802.11 there are retries because packet error rates are expected over wireless. So most other link protocols, non-wireless, don't they do all the retries at the transport layer. And I think the MCS PHY rates, and with Wi-Fi, there's so many choices to choose from. So the probability that a PHY rate engineer has the optimal MCS for the channel conditions is extremely low because it's impossible to figure it out in real time in the time frame you have. So it's a best guess into a massive table. We talked about the media access variability, and then it's also half duplex. So that's just the nature of Wi-Fi. It's half duplex. There's a power imbalance between the AP and the stage on all mobile, and that allows the AP to transmit at higher rates and higher MCSs. So the channels actually, because of the power difference, you have different performance directionally. It also causes the need for this RTS DTS, where the AP kind of tells everybody, stop transmitting. I can't hear that remote device. Please stop transmitting. So that's in play too. And the other thing is, since the clients tend to be on batteries, they have power save modes. If they're not, transmitting, they go to sleep, and so they expected the AP is going to store things up. So if you're a transport and you're trying to send, you think their clients there, interacting with you, actually it probably went to sleep, and you're dealing with an AP that's queuing for you. And then finally, the TCP ACKs are actually expensive because they're usually relatively small, and you consume a TX op to send an ACK. So play that. Just a reminder that in a MIMO model, that the RF conditions are variable, and here's the transfer matrix of how a signal gets through, and it's a massive amount of signal processing and variability. I won't spend too much there. Okay, so what we look at are sort of throughput vectors, which has been, or the capacity, which has been a focus. Some of the things that affect throughput are the channel, the QAMs and spatial streams, the MCS, the channel bandwidth, aggregation, how many packets can you get in and transmit, the packet error rates, and the biggest one actually, or a big one that's relative to CC congestion control, is this software FIFO empty. That means that Wi-Fi MAC stopped aggregating because the transport didn't give it enough packets. So what the MAC wants to send an aggregate, and if there's not data ready to be sent, it stops aggregating, and that really impacts throughput. And there's something called frame bursting. I won't go into that too much. And then what air competition, which is a misnomer, which is meaning that there's others using this channel. Trying it there. For latency, it's very similar. That you'll hit, but other vectors. So it's very similar, but not exact. And one of the primary ones that's different is these EDCAs, and how do you get access to the MAC? So if you try to access the air, or if a device tries to access the air and there's other devices, it just has to wait. It has to get behind, and then it plays this probability, throw the dice game, and I go again, and that's just what happens. And so you back off based on the EDCAs primarily. And the direction matters. Typically, a client device actually does flow control at the driver level, but then the other direction is going to be more at the CCA level, because it's not closed. So if a medium's, the driver gives flow control feedback to the transport in upstream direction. Downstream direction, that can't be the case because you're not on the same link. And the differences in the power again. Multiple has more radios, so you can do multi-user with the AP. And the other thing is, one-way delay does not equal half an RTT. I mean, so if your algorithm decides, oh, I'll use RTT and divide by 2 and say that's my one-way delay, well, you're completely, that's wrong. It's just wrong. So that's just a given. And I think that pretty much covers here's an idea, just an eye chart type slide, but this gives you an idea. When we have a throughput problem, these are all the characteristics and distributions we're looking at to try to figure out what was causing the problem, and we'll have similar analysis for latency. This just shows you the complexity of what drives throughput on a wireless network, and it's all distributions and probability of various events. And I think that covers it.
Fascinating. That is a lot of considerations. Do we have any questions for Robert? Okay, not hearing any right now. Maybe Simone, did you? Oh, Doris has a thought or question.
Yeah, sorry, I was trying to look for the button and also try to formulate the question. So, this is really insightful, both of you. Thank you. It leaves me a little bit depressed because also, like, I think I've seen a presentation similar to this like a while ago, and it was bad then, but this is worse in the sense of the complexity. And it seems like as we squeeze more bandwidth out of the medium, these lower layer magic things just going to get more and more complex. And I wonder if is this just a given, or is there any? Do you see an ability to reclaim some sort of sanity? Because I really wonder, like, whether we should just ignore all of this because there's no way we can do anything about it, really. Let me leave here on a positive note if you can. Thank you.
Yeah, I guess. Do you want to say something, Robert, or?
Yeah, I agree with that. I mean, if you look at the standards, I mean, I feel sorry for the fire rate engineer. I mean, they have, in the microseconds, maybe 10 to 100, so figure out into a table that keeps growing by the standards guys. Like, let's add some more choices here and some blah, blah, blah. You're like, come on, man. So yeah, no, it is. The complexity is going through the roof, and it's hard to actually achieve it. My view is reduce the complexity, and mostly through physical way you build your wireless networks, and try to get a little more predictability in the channels through physical design.
I can perhaps add that I started mostly around this working with radio in 2010, and then the issue was that most of the stuff that we did was like essentially what you call full buffer. You have infinite amounts of traffic that you transmit on the radio layer, and then everything works fine. But eventually, over time, it became clear for many people that we have an internet that you need to address with packets of or objects of varying sizes, and you have request response things, and 4G at that time didn't address it. 5G starts to address it. You have things like configured ground scheduling that you can use, and also you can use pre-scheduling and in order to increase this request response behavior. But then there is always, I believe it's not much different. There's pretty much the same physical challenges with Wi-Fi as 5G and what you call 6G. And you preferably should have a bunch of data to transmit in each slot to utilize the spectrum efficiently, and also utilize for energy saving. So it's a bit of a you need to trade things here. So
Sorry.
Yeah, Gary Fairhurst. Thanks for finishing on that one, Ingemar, because yeah, I mean, okay, so story first, and then I follow up on exactly what Ingemar said. We're trying to do DSCPs, and we see things in Wi-Fi, and we go, oh, well, there is a kind of impact here on the Wi-Fi configuration if only the IETF had that interface or knew what to do. And we're moving from a world where things were 10 times faster to maybe 1,000 times faster. I mean, like there is such a dynamic range in the things we're talking about. This becomes so awkward to know what to do. What can the IETF tell the radio or Wi-Fi that would really help to get a better service from it? Does a diff-serve code point help? Would it help to give you even more? Would it help to tell you something about the session? I mean, surely some way we can get these parameters in a more sensible place for the sort of traffic that's going over. I mean, is that wise? Or do we just say, no, you move packets and packets are it? Can we help?
Yeah, one thing that is there in the driver is the SK pacing shift, which kind of affects the aggregate size. So that's sort of low-hanging fruit. Try to give Wi-Fi an aggregate because the TX op, we're really, and I argue with Wi-Fi 802.3 packets are an artifact. We want to transmit 802.11 aggregates. So help there. How do you get aggregates out? And that's one thing I think that could be better done.
Okay, can we just clarify what an aggregate is? I mean, do you mean you just want lots of packets all at the same time so you can send them all together?
Yeah, not lots, 32 to 64, depending upon the chip. I mean, it's just how much.
Yeah, yeah, and all the other talks say we want to use pacing to get through other parts of the internet. So immediately we have an interesting trade-off yet again.
Yeah, exactly. Yep, exactly. And by the way, by getting an aggregate, you actually, for the aggregate, those packets are going to get lower latency because the TX op is your gating factor. So if you say, oh, I'll start pacing, well, guess what? You start burning your TX ops.
Yeah, I want to point out that, well, repeat the comment that this is actually an intrinsic problem. Batching always raises the efficiency of hardware and always increases the jitter, and it increases the jitter to everybody else on the network. And one of the things, the BBR 125 CWIN gain actually came from measuring LTE performance. And so we've got a problem that the people up the stack are measuring down the stack. And guess what? The people down the stack are measuring up the stack. And the people down the stack are typically measuring with older stacks. People who are measuring down the stack are measuring with older implementations. And I'm aware of at least one case where this has caused, actually buffer bloat is specifically a consequence of two different measurement experiments coming to conflicting results that didn't work in the deployed internet. We need to design the parameter which affects that trade-off, an engineered global optimization on the trade-off between burst size and jitter. And it needs to be different for different traffic classes. And I don't know how to do that. This is sort of the start of a conversation that could lead to that kind of thing. But it's absolutely true. The network is more efficient. The hardware is used more efficiently if the data is burst at the consequence of more jitter. And we need to do that. We need to design it. So this is excellent work.
Jana Iyengar, 2 points. One of them is that I don't think it's lack of pacing, but it's about the quantum that you use when you're pacing, right? I mean, that's always a question that we've always wondered about. Is it 2 packets, 4 packets, 30 packets? And this gives another data point about what exactly it should be. It's not universal, but that's part of the problem that Matt is talking about. We have to, the broader point I wanted to make here is the complexity is there, and I agree with Lars. I feel a bit depressed, and I was just looking at this and going, are we back talking about problems that we talked about 20 years ago. And what does that, I mean, part of it reflects on the fact that we haven't fully understood how to take all of this complexity into account in building our things. And so what we often do, and I don't know if this is the right answer, but what we often do is we paper over this complexity, right? We use measurements, we discover properties that are important to us as emergent properties of the network, and we rely on those to design our congestion control principles. That's certainly one way of doing it. It's the way that we've worked. We worked so far because the only way we really understood how to do this in a complex system like this, and in a place where time scales are so different across these different layers in terms of development, deployment, and so on. But maybe there's something more we can do. I mean, I'm certainly open to exploring more sort of combined things. We can call it, I don't know what we want to call it. We want to call it plus if you want to combine with the network stuff. You want to call it, what is the thing that we used to do, like cross layer all the way down to the thing? What's that? No, well, that working group was not called Get Depressed, but we could call one PILK. Thank you. We could go to PILK again. But I think the question here is, through this complexity, which parameters, which pieces are actually useful and meaningful, given the timescales of decision making and timescales of variation across the different decision makers. So there's a local one, there's the end-to-end one, and so on. But yeah, I mean, it is a hard problem, I would say.
I'll make one quick statement. I think a lot of the Wi-Fi complexity has been sort of hidden to CCA engineers because pre-pandemic, everything was last mile limited. So the fact that Wi-Fi outran your last mile link says, I don't care, because the congestion control, I was finding it that bottleneck there. But then pandemic, and we went to gigabit per second, and then you're like, oh no, it's no longer that link. It's the Wi-Fi links, and that's a highly variable link. So now it just opened up, okay, to the depression element of this problem. You just now you get to see it. Before you were hidden behind the last mile link. That's no longer the case.
Jahid, I was seeing everybody getting depressed, and I was thinking, like, let's use the AI to do the things that we want to do. But yeah, so
just realised that I'm getting old, but the PILK thing was 3819, which was trying to say how the network interacts with the lower layers, just in case people have missed that whole context. Oh, you did you?
Yeah. So the main reason I came up is, like, I think I wanted to say, like, what Matthias already said. Like, there was, like, when we were doing this kind of congestion control and try to understand and doing, like, when I was doing simulation, I was changing the how the application model in the simulator, also like how the network elements in the simulators, all these things in 2007 to 2016, or every time I did that. So I think this is a continuous process, right? So we have this kind of problem, like we end up with, we come to solve a problem from different sides, and we start to, we do things based on lots of assumptions. But I have something to talk about a bit about this congestion control simulations. I think that's really what a lot of people do here, right? So when I was doing in 4G simulation, there was, like, people coming up doing the radio, like, so get through the mobile telephone, get some data dumped, and they put that as an input to the simulator and do develop congestion control. And I have been telling, like, don't do that, because in radio, especially in 4G, if you actually don't use the bandwidth, somebody will take it. I just wanted to know, Ingemar, do you have any comment? Like, is it getting better or worse in 5G? Because these are the things I think we should be popping up here so that people don't do the similar mistakes.
Gilmore, feel free to respond if you have an immediate response. We're running out of time. I locked the queue. We're doing our best here.
Leave to Stuart or Randall, or who is it?
This is Stuart here. Couple of quick comments. Ingemar talked about small buffers and big buffers. And I know what Ingemar was talking about, but the reason I caught on that is that it's something I hear a lot of people talk about and ask. I remember when Van Jacobson gave a presentation at IETF about FQ Coddle. He had a really good description, and he called buffers shock absorbers for the internet. It's not that buffers are bad. It's not a debate whether they should be big or small. The purpose they serve is to smooth out bursts, because traffic is often bursty. Wi-Fi aggregation makes traffic bursty, and you want a buffer to smooth that out. When the buffer never drains to empty, then you've got too much in the buffer. So when people try to tune their buffer sizes and it's too high, the latency is too high, and they make it too small and the throughput suffers, that's because you can't answer this question in terms of a fixed size. You need to be making predictions about the future, the way Pi does, the way Coddle looks at the last 100 millisecond window. So it's not that a certain size is the right size for a buffer. If it's small but growing, you want to tell the sender to slow down. If an aggregate arrives at the Wi-Fi layer and suddenly you've got 50 packets at once, that's not a problem. That's not suddenly a queue that's too full. If 50 arrive and then it all smoothly drains to the output interface, that queue is doing its job. So whenever people talk about big queues and short queues, I try to correct them that it's not, you can't answer this in terms of fixed size. So that's my comment about queue size. Thank you, Bob, for presenting some of this information about all the complexity in Wi-Fi. I know IEEE is meeting next week, and I would love all of us to try to work with the people in IEEE to work out how we can work together as partners to solve this problem. Because I get very frustrated when I hear IEEE people tell me, oh, round trip delay, that's a layer 3 thing. It's nothing to do with us. And I have to tell them, milliseconds don't respect your OSI 7 layer model, right? Milliseconds add up at every layer. You can't say it's nothing to do with us. And somebody at the microphone said, do we do pacing? Do we not do pacing? And it's a similar comment I made before. It's not a binary yes-no thing. We need to work with the Wi-Fi layer to figure out richer interfaces between the transport protocol and the link layer, so that Wi-Fi can do reasonable aggregation to get good throughput, but not so much buffering that it adds delay. And that's a partnership, and it's not something either of us can do in a vacuum.
Thanks.
I reiterate that what Stuart's saying. I do think that the IEEE and Wi-Fi and IETF congestion control, there has to be cooperation. I mean, we can't solve this without that kind of cooperation.
I'll keep mine. Randall Jessup, Mozilla. I'll keep mine very quickly. I know we're short on time. This may be unworkable. I just a thought that occurs to me when I was hearing all this is that we already have an issue with the interaction between things like GSO and pacing and so forth. I'm just wonder if it's possible to in some way be able to present the Wi-Fi layer with a whole bunch of packets and have it get paced out on the other side in order to abide by the advantages of lots of data at once over the Wi-Fi link. That's basically it. Just a thought.
It's me. So I just want a quick question. So you guys have been more on the vendor sides and maybe closer to who is working on standardization of 6G now and Wi-Fi 7 and where this is going. Do you see anything changing in terms of the way they are doing work when you talk about throughput and latency, or this is just the way things always were? At least I know from 3GPP, but not much about the IEEE.
I think as regards to 6G standardization, I believe it's the awareness of the general internet is much bigger now than it was 4G and even 5G. So I believe it's more like, I believe IETF has a quite big role here, and I mean, especially for discuss things like this, and I believe there is a value exchanging information between, for instance, in this case, 3GPP and IETF.
For me, one of the biggest things that's impacting Wi-Fi that we've got to figure out is latency versus capacity. We've had these big numbers on retail boxes that say, one number does, X gigabits per second, and then, okay, that's what they're going to pick. And then you find out, well, it's a latency problem or some, the complexity of the domain. So they didn't get what they thought they were going to get. And so I think that's a problem. I think we've got to get latency. And I do think the lack of sort of Wi-Fi expertise into IETF is a big problem. There's just not a lot of Wi-Fi people coming to IETF. And I don't know why that is, but as a component supplier, we say we're just a component person. We just move frames. We don't care about what's above us. And so somebody has to change that. Maybe it's a system integrator or something.
Yeah, and I really want to stress trying to get away from cross-layer measurement and instead do cross-layer co-engineering. And sort of the first question I would have for lower layers is what is the optimal backlog or the optimal peak backlog to make sure the radio does things, because the buffer occupancy is always going to be a sawtooth. The goal of all the control systems is that the minimum queue depth is fairly small, but how high should the peak be? And because that's sort of one of the parameters.
So, I mean, we got magic numbers like 13 milliseconds for that. Okay, we always want to have 13 milliseconds worth of stuff. And that's to get your max capacity number. And so you're like, okay, but do I need that? Do I really need the max capacity? So, and it's a magic number. It's some engineering lab with some consideration, and they come up with this. I think works the best.
So this was actually measured after the design was implemented.
Yeah, the firmware.
Right,
in the firmware,
right.
is saying, okay, how much is it? With a specific operating system on a particular handset, right?
Because you could easily tune a transport like BBR to deliberately cause 13 millisecond queues. And it would be interesting to see how different that was, and whether or not for best effort traffic, 13 milliseconds is a problem. I'd probably pick 15, but
I don't know where 13 came from. I don't know. It came from measurements.
Right.
And it probably
But that's what I mean by co-engineering is it's really important going forward that these problems not be solved by ad hoc measurements, but are actually chosen.
Definitely.
We're over time, right?
Yeah, we are over time. Ingemar, did you have any last?
I guess for 3GPP access like 5G, then can come up with a magic number. I believe a few milliseconds is mostly enough, because we have tried with a TTP prog actually, and if you inflate the low marking threshold to a couple of milliseconds, we actually managed to use up the link capacity like 100%.
Right.
Could be some glitches if acknowledgements are delayed in the uplink and then the transmission stops. But with a few milliseconds, what you call queue or a data available in the queue, then you manage to fill up the transport blocks efficiently. So,
and
but
a footnote
I can't say a magic number here, but yeah.
And a footnote to my previous comments about fairness, I actually think this problem is more important than the fairness question.
Right. Okay, so we are over time, but this was an excellent panel discussion. I'm very grateful to the presenters as well as everybody who participated in the discussion. And I think this is a great use of our time in ICCRG. Please let the chairs know what you think. And I hope to see everybody at the next ICCRG meeting. Thank you ever so much for being here.
Thanks a lot.
Thank you.
Thank you.
Have a nice weekend.
Yeah, you too. Thank you, everyone.
This brings back memories.
Yeah.